So please raise your hand, the ones that have solved problems with beams before. I strongly hope that every mechanical engineer have raised your hands at this point. Got it, 3, 4, 5 people. Okay, it is a good start. Okay, so rather than me giving you a lecture about beams, because beams is a very complex theory, there are many books about beams. We're gonna simulate one simple beam, okay? And if there are questions about the theory, we're gonna cover them on Wednesday. But today we're going to go hands-on on COMSOL and try to solve those problems here. So little overview about what we saw, just quickly. Can you see my screen?
Yeah.
Okay. So remember, we covered the Hooke's law. We talk about springs and how the force is equal to the spring constant and the distance that we are having, multiplied by the distance that we are having. And we saw how the springs in series and in parallels can help us calculating the spring constant for multiple problems, okay? And we end up doing the parallel and serial springs for this spring system, 4 spring systems suspending a mass. That's what we are gonna simulate in the second part of the course today. And we discussed that, hey, there is something called the Young modulus that compare a stress and a strain, and it's the ratio between the stress and the strain, and it's a magnitude and a property of the material itself. And you can apply that using the Hooke's law that we already discussed before, okay? Where the stress is a relationship between the force and the area, and the strain is a relationship between the initial distance and the change in the distance. But we didn't discuss about a beam. So a beam basically, or a cantilever, as we call it in MEMS, is a piece of material that has been suspended in one of the edges. And it's a fixed constraint. It means that is not moving. I mean, that part is not moving. And this is a cross section, okay? So cross section. What we are expecting, it's applying a force in this point and see what happened with the beam. Ideally, the beam is gonna deflect. This is what we are expecting. If you apply a force at the end of a ruler, the ruler is gonna start bending, okay? And if we know that our force it's equal to a K, I'm gonna put that point force here. It's equal, or in the negative direction because the force is going down, a K multiplied by X. The big question is, well, okay, what is going to be the K of my spring itself? And that spring and that solution, what is this K? It's not as easy as we thought. And then we need to represent the problem into the governing equation. So for those of you that you have worked with beams, do we have a question? The governing equation is going to be the Young modulus multiplied by the second moment of inertia. And it's this problem of the governing equation is going to be a differential problem, a second order differential equation. So it is a matter of the position X and where this is X and this is Y. Regarding to Y, what is the position in Y for this problem? Where this is related with the beam cross section. And at the end, this is going to be equals to the moment of inertia or the bending moment. okay? One amazing source where you can learn this, it's going to be a book called Rourke's Formulas for Stress and Strain. I'm gonna present that one. But how is this connecting with the beam? Well, if we do that derivation and based on that cross-section, we're gonna find out that the K for this problem, it's going to be 3 John modulus multiplied by I L cube. And what is I? Well, I depends on the cross-section. So I'm gonna have this one here. What is I? I for, if the cross-section of this is just simple, a square beam, and this is gonna be A, and this is gonna be B, okay? My I is going to be AB cubed over 12. This is for a square section. Okay. Okay. So I am not doing any derivation here of this. This needs to be done by yourselves. You need to read the chapter number 4, go to the Rourke's formulas for stress and strain, and find out what is going to be, I mean, how do you get to this moment of inertia? The other thing that is important is that if we solve this, we solve the delta X for this problem, it's going to be force multiplied by L, look, the L cube here, L cube, divided by 3, multiplied by the Young modulus, multiplied by the moment of inertia. Or the moment of inertia of the square, okay? So this is at the end. If I am trying to answer the question, what is my delta? Oh, I think, I mean, delta X and delta Y, if I put it in that way. Sorry, this is with delta Y, X and Y. And in this coordinate reference, this is gonna be Y, okay? So I'm just giving you the equation, but now let's go to COMSOL. This is just, have it there. We are gonna need it. This is the analytical model that we are looking for. Analytical model for this one. So let's imagine that I don't know, and I wanna answer this with my simulation. So first of all, raise your hands if you have ever, let me stop. If you have ever worked with COMSOL. I think it was like 30% of the cars, 35% if I remember correctly. 4 people. Okay, so I'm gonna start from scratch with COMSOL. And the first thing is, what is COMSOL? So COMSOL is a software that allows us to solve differential equations. You saw that the problem of motion and deflection of the beam is a differential equation. If you have, and let me share my screen. If you have a known area for the beam, you can go and look at one of these books. This is the book that I was suggesting, the Rourke's formulas for stress and strain. And this is just dedicated to beams and just dedicated to how to calculate the stress in a beam and in different types. So if you go here to 309. Then
Professor,
you're gonna have a, sorry?
So, Professor, do we have this book available in the library?
Yes, we do have this book available in the library.
Okay, and also, could you please mute? I think someone has the microphone on and it's there is a lot of noise and it's very annoying.
Is it me or?
No, I think it was another person.
Let me mute everybody. Sorry for that. If you want to talk, just unmute yourself and. Okay, I think that's working. So yes, this book is available. I'm gonna put the link in our website. And if you are looking for a cross section that looks like this, the formula for the inertia is here. Okay, if you're looking for a beam with a load in one of the corners, you're gonna find, well, you need to find this carefully, but look, all the cross sections are here, and where to apply the forces. Yeah, they're here. So if you want to apply the force between two beams in the center, you're gonna find the model here. If you're gonna apply a force, a torsional force in the center, so basically making the torsion of a beam right in the center that is clamping two areas, they are gonna provide the formulas here. So it is a nice guide of where to, how to solve that problem analytically, okay? But let's continue with the beam. We are gonna, for solving this, we need a second, the differential equations. To solve the differential equations, we need some program that help us calculating that one, especially if we're doing very complex geometry. COMSOL is that software. COMSOL solves partial differential equation using the finite element modeling, okay? What does it mean? It means let's divide the problem in very tiny pieces that we call, we create the area, we recreate the area in terms of a grid. So we make tiny squares or tiny triangles out of each block, and we try to solve the differential equations in that area, in that point, okay? For doing that, we need some boundary conditions. So all that we're gonna see today is how to define these boundary conditions and how to create that simulation. I'm gonna start with a very simple problem, but COMSOL, it's a very complex tool. I like to make the equivalent between COMSOL and MATLAB. If you remember, have you used MATLAB before?
Yeah.
No, nobody. I saw one nod, two, yes, like two nods. Okay, MATLAB, it's a complex software that you cannot tell, like, I fully learned how to use MATLAB. No, why? Because it has so many libraries and so many small pieces, and people start coding and adding sections to MATLAB that you overall learn how to navigate through MATLAB. But if you want to do optimization, you download the library or you use the library on MATLAB for optimization. If you want to do control, you do the library for controls in MATLAB or the Simulink library in MATLAB. So you go and specifically learn the piece that you need to learn. Okay. Now, let me jump into, okay, and this is the first time that I tried this remote on remote desktop. So please let me know if it works. I hope we are not going to have any trouble with this. So I'm going to try to share this screen, and as soon as I start sharing, I'm going to lose your faces. Okay. So please, if you have a question, talk to me. I need to hear from you because I don't see my second screen as soon as I start making this share. Okay. Can you see the second screen?
Yeah, we can see this.
It's supposed to be a CVC and 4 files.
Oh, yeah.
Yeah.
Great. So this is working. So the idea is try to open COMSOL meanwhile I'm talking and try to do the same that I'm doing. Okay. And let's see if that works. If not, we're going to change the strategy on the fly. But right now I'm going to be an overall indication. So the first of all, this is the symbol for MATLAB, for COMSOL, sorry. Class kit license COMSOL multiphysics. Again, as I mentioned to some of you, you are not going to install COMSOL in your computers. In our university, we have licenses dedicated to laboratory computers, okay? So usually this class, we will have it in the lab and everybody will do the experiments in the lab. But right now we're trying to do it virtual. So let's open our console. We just double click here. And as the name implies, it's a multi-physics problem. It means that it can solve multiple differential equations from different modules. It means we can solve chemistry equations, mechanical equations, thermal equations. It doesn't matter. It matters that are differential equations. Rebecca, I saw your hand raising.
Yeah, sorry, because I had problems with the installation, and I don't know if we are going to have access to this icon to open the program once we connect to a remote computer. I didn't understand how it's going to work.
Okay, so let me go with you. First of all, you need a VPN just to access your VPN in your computer. And as soon your VPN is running, you are not going to install COMSOL in your computer. You are going to open a remote session of a computer that has COMSOL already.
Yes, but yeah, I access the web that says remote computer access, and there you see a list of available computers. Then you have to go there each time and connect to a computer?
Yes.
Okay. And and then download the work that you do?
Yes. Yes. So you can copy and paste from any file that you make there. Let me give you an example. I opened this one. This was the one that I was working. You connect remotely to that computer.
Okay, so each time you download a link. So sorry if everyone else know how to work, but this is my first time and I'm very bad with these kind of things.
No, don't worry. Give me 1 second. I just need to open. Supposedly, let me share my screen 1 second and let's see if this is gonna work. Okay, supposedly, in every computer, once you open a session, it creates a common folder. So if you create a folder called CDC in this computer, you can open the same folder in other computers. This is how it should work. And you need to test this and try to open it. It doesn't matter. You can just simply copy and paste things here from your own computer. You can copy the file and paste it in that screen. So for example, if I make, let's say this file here, I copy and I can paste it in the other screen. That's it.
But the other screen is the other computer, right? The remote one?
Yes, yes. I open the remote one. This is the remote one. And I can paste everything here. So it's like having another folder open, but this is a virtual machine. This is a file in the remote computer. This is a file in the remote computer, but I can copy something from my own computer. This is my own computer. I can copy this one with Control-C, Control-V, and paste it there, okay? So your COMSOL, the COMSOL is gonna open all the time here in the remote desktop, and you can have a folder here with your own simulations, and then copy and paste them into your computer afterwards. Okay, so let's open COMSOL. Let's double click here. Sometimes it's faster. I don't know what happened. Oh, sorry, it's in the other screen. Okay, now you can have two options. Rather using a wizard that is easy, I recommend you to do that, or just start from a blank model. Let's use a wizard. And from the wizard, COMSOL is gonna ask you, okay, what is your problem? Your problem is a 3D, a 2D, an axisymmetric, or a 1D, or a point problem. We're gonna do now, we're gonna do a 2D simulation, okay? Even if it's a 3D problem, we're gonna do a 2D simulation because it is easier for us right now and it's faster to compute. So in COMSOL, do not try to make the most complicated simulation at the beginning. Try the fundamentals. Start from something easy. Let's try to do a 2D simulation, and you double click. These are all the physics that you can simulate in COMSOL. You can simulate from AC, DC, magnetic, electrical, wave, particle tracing. You can try to simulate acoustics, problems with waves, problems with ultrasound, pipe acoustics. You can also try chemical, so chemical reaction, problems of transport, moisture flow. You can use the fluidic flow, and we're gonna use this one later in the course, particle tracing, single flow, two flows, two phases flow, fluid and structure interaction, thin film flow, heat transfer. You can go on all these ones. Optics, radio frequency, this is very useful for waves. And the one that we're gonna try to solve is mechanics. Those are not all the modules. This is the light version for a student environment. If you are doing research on this or you are working in a company, more likely you're gonna have additional modules that you can purchase, okay? But that's part of their game. So if you have any question, I encourage you to, well, ask me first, and then we can go and visit the website. Because there are many modules that we can have there. Let's gonna check the solid mechanics for this one. And again, I'm sorry for the three of you that already work with COMSOL. This is gonna be too basic. If you want to start jumping into the second question of our problem, go ahead. Don't pay attention to what I'm saying, and I'm gonna create another, you can start working in the second part of the module meanwhile we arrive to that point. Once you select solid mechanics, then we need to select a study. What are we trying to analyze in COMSOL? Are we trying to use agent frequencies, frequency domain, or stationary? Right now, we are gonna try to do an stationary problem. We are not gonna do this time dependent. We just try to know what is the deflection of a beam when we apply a force in the tip. That's the entire question that we have right now. So we go for stationary. And now this is the COMSOL environment. So what do we have here? By the way, do you see my mouse when I am moving the mouse in the screen?
Yeah. Okay.
So you have on top of this, you have the bar that has many options. That bar is gonna be changing depending on the tab that you are applying here. Don't worry about that one so much. Those are kind of easy access buttons, but I'm not gonna discuss them right now. It's just know that the easy access buttons are on the top. To be honest, I don't use them very often. The one that I really use is the model builder. And this model builder works a lot like SolidWorks. If you wanna build something, you're gonna start adding steps on top of the existing ones. So once you add a step, you can remove the step of move it forward or move it backwards. For each section here, I'm not gonna describe right now this one. For each section, the settings are gonna be changing. So you notice that if I click any of this, the settings on the middle are gonna be changing. And what you are having on your right, the graphics, it's displaying what you are doing, okay? So the steps that you follow in COMSOL are the following. You first define, I'm gonna put it like this. And this is a very good order that COMSOL does these things. Is first of all, a component means a piece of simulation that you want to fully packed. So for example, if you have a combination of materials or you have a gear and you want to simulate that gear, you're going to do it under the same component, okay? It doesn't matter that the gear has 3 materials on it and then you're trying to do thermal on one part and perhaps mechanics on the other one. No, if the full body represents a complete simulation, you do it under the component. Most of the time, 99% of the time, I do one component simulation. I don't require to make more than one. But for complex things, you can open more than one. You first make some definitions. For example, let's say I'm gonna right click. Let me add, what is the initial force that I'm sorry, here in parameters is here. Here in parameters, global definitions. I'm gonna say, okay, my force in Y, and it's going to be 1 millinewton. That's the first parameter. You can give a description, is initial force. So how did I assign 1 millinewton? Is first the number, and then in square brackets, you put the magnitude. Because it does, I mean, COMSOL doesn't know what is this. This could be in meters, or this could be in millijoules, or it could be in whatever. You need to define what are the units that you are gonna be working. So 1 millinewton in brackets. And now we're talking about force. Now COMSOL understand the magnitudes. And this is very interesting because in COMSOL, it's not only about numbers, it also combines the physics of it. 1 millinewton, that's the maximum force that we're gonna apply. Okay, now let's go, we are not gonna do any definitions, let's go to geometry. So let's stop in geometry. And the length of unit that we are gonna work is going to be microsystems. We're not gonna, I mean, we can talk about simulation of stars here or black holes, but right now our units are in micrometers. So everything that we write, and look how in the graphic section, immediately in this corner, all the magnitudes change to micrometers. If I go to millimeters, everything changed to millimeters. So leave it in micrometers. That's a preferable area. We expand a little bit the geometry, and now we want to draw something. How do we draw? We right click, and we have a circle, an ellipse, a rectangle, and a square. Let's go by a rectangle. Let's add a rectangle. You can change the names here. For example, this is gonna be your beam, if you want. And define the geometries of the rectangle. This is gonna be a 100 micrometer in width, and in height is gonna be a 5 microns. And where is the position? You can define the position in the center or in the corner. So let's go in the corner in the position 0, 0. If you hit build selected, automatically it's drawing the rectangle that you set. Look, 5 microns in width and 100 microns long. Okay. If you want to change the dimensions, you or move it up or down, you can build selected. What happened? Oh yeah, I move it in X. Sorry, I was thinking that I move it in Y. I move it in X, for example, 100 meters, 10 microns, and now it's moving the block 10 microns top. Or if I play it 0, it's gonna be in the origin, okay? I am going to move this minus 5 microns in Y. Why? Because I want this point, this top corner, to be the 0 of the problem. Okay, so if I move in Y a direction, it's gonna know that this point, it was 0 and not 5 microns on top. It's just a coordinate system. Okay. So that is the geometry. Today is just a simple the geometry. You can do geometries in 2D and in 3D, but usually you start from a 2D plane and then you build up.
Professor?
Yes, Paul?
Just a quick question. So it seems like the reference point is the lower left corner of the geometry. Would there be a way to change the reference points when moving the shape that you built?
Yes, yes, there is a way. So you can go here and instead of doing in the corner, you can do right from the center. But the reference coordinate of the entire simulation is gonna be this 0, 0 point. You see here the 0 and here the 0. This point is the absolute reference for your entire system.
Okay, I see. Thank you.
So let's leave it here in the corner. Now, if you have more modules, more blocks, instead of building the selection, you can say build all the objects and then automatically build absolutely everything. But this is very useful if you have made only one block. It's very useful just to find out what is happening in that specific step. Now, the second part is adding my material. What is my material? What I'm working with. The nice part of COMSOL is that it has an integrated library of material. So you can say like add material from a library. And now you're gonna have the library here that belongs to many, many materials. Usually we're gonna work with the MEMS materials. And you can have, this is gonna be a semiconductor, and I'm gonna work with a polysilicon, polycrystalline silicon. That's gonna be my build. Now, here is the question. If the material is not here, where can I find this information? That is the tricky question, because it means that you need to go online, search in the literature, especially in papers or in books, and find those values, or do an experiment in your lab and test that parameter, and you go and input the parameter here. Most of the common materials are here, and for the common modules are here, but if they are not, you need to search for them. And that is where COMSOL became very interesting. Right now, we're gonna work with a density, a Poisson ratio, and a Young modulus equals to the ones that the literature provide, or some references provide, okay? But those are not all the picture, okay? So for example, if we go to the definition here, this is the definition for that specific material. You can change it afterwards. Yes, you can change it afterwards. And the properties not only can be more than just a constant. You can load an equation here, or you can load a graph, or you can load a function. So this is gonna be very useful. Now I select the polycrystalline, but I didn't select what was the material that I wanna talk. So this beam is gonna be a polycrystalline. Perfect, problem solved. I'm gonna hide this material to have a little bit more space. Now, what are the physics that we're trying to solve? So the physics are going to be solid mechanics. Those are the physics. There are some general, if you click in this tab, you're gonna have a general parameters for the solid mechanics, starting from the equation that we are trying to solve, okay? So the equation that we are trying to solve is gonna be presented here, or if you go, let me see, usually, I'm gonna show you, I'm gonna show you later where to see the more complete equation. Right now, let's continue on this one. One of the special parameters that you can change here is the thickness. Okay, what is the thickness of this beam? I'm gonna make this beam a square beam, so 5 microns by 5 microns. So in this moment is 5 times to the minus 6, because this is microns, okay? Look, this thickness parameter is in meters, but by defining 5 times to the minus 6, I'm defining it in microns. So it is important that you write that value here, okay? So right now, even if it's a 2D simulation, it's telling me that there is a thickness associated with it. So that is the third dimension that we can use. That's why a 2D simulation for this simple problem is enough. And now, this is the overall equations that we are trying to solve. If you have a question regarding the module specifically, I encourage you to go to the help. COMSOL is very good at providing help and providing guidance, especially scientific guidance to different problems that you are solving in the modules. So it is a very good practice to go to the help and answer it. This help menu is based on where are you located. If I am here in materials, it's gonna give you information about the materials. If you're in solid mechanics, it's gonna give you about this one. If you read this first part, it's gonna tell you that the default material is a linear elastic material. It's linear, be careful with that. It's linear elastic material, okay? And it's telling you what are the approximations that you are making with this, okay? And what are the equations that you are solving with this, okay? What is the thickness? Why the thickness is useful? This is the step that you cannot miss as researchers and as graduate students. Or if you're gonna work in a company, you cannot miss the part where you read what is the type of simulations that you're doing. Right now, I'm telling you, this is the simulation that you need to be running. Why? Because I already know that this is the structural mechanics, and those are the equations that you need to be doing. But look, here is the quasi-static problem, the structural transient behavior, but I need you to, for each module that you're gonna simulate, you need to read this help. You need to find out what is the COMSOL doing, because every physics is gonna be different, doing something different. This is not generic. This is specific for the module that we're working on.
Sorry, a quick question. So this is, this information appears after you configure all the parameters that we have already introduced, or is general information?
It's general information for the specific module that you include. So instead of solid mechanics, you add another physics. For example, I add another physics, and that physics is going to be AC/DC. Let me see, magnetic field, no current, whatever. I'm gonna add it here. Look, another physics instead of solid mechanics appear here, magnetic fields, no current. If I ask my help button, now the parameters that are asking is about the magnetic fields, no current. And they are talking about the Maxwell equation, and they are talking about how the current involves, what is the thickness for this problem, what are the boundary conditions for this problem. So it is dependent on the specific module that you select, not the parameters. It doesn't matter if I type here 1 millinewton or not. It cares if I am using the solid mechanics or the magnetic field no currents. Does that answer the question?
Yes, I just was wondering if the software somehow tells you if you enter like something wrong. I mean, no. I guess that when you run after running the simulation, but you know, like you go in step by step, entering your parameters and everything, but there's something that it's impossible. It's not realistic. So that's the software tells you.
Very good question, Rebecca. No. Basically, this type, not only with COMSOL, with any multiphysics simulation like ANSYS, Abacus, even SolidWorks. Garbage input equals garbage output. If you put garbage, it means I make a force of 3 tons on the top of a micrometer beam. COMSOL is gonna try to simulate it. And he's gonna say, like, do it. I mean, this deflection is not, should be this one. Is that feasible? No, long time ago, the little beam broke. Who can tell if it's good or not? You. Each of you, when you simulate, need to pay attention to that one. And that is why we're doing this course, because it's not an easy task to do it. So let me continue doing this simulation, and you are gonna find out the answer for that question, okay? I'm gonna remove the magnetics here. I'm gonna change the parameter. Instead of 1 millinewton, I'm gonna change to 10 millinewton, because I wanna show Rebecca what is happening if you put an incorrect value. Okay, we load the properties of the material, we load the solid mechanics, but now we need to define the boundary conditions. What was the boundary condition for this beam? We said the first one, and when you want to add a boundary condition, you right click. There are some boundary conditions that are defined already, like this is the linear elastic material, okay? Everything is free, and the initial value is 0, like start without moving. Everything starts in the air without moving. But if I need another condition, for example, I want a fixed constraint. It means this is attached to a wall. So I give fixed constraint, and I select the domain, the boundary that I want to add. So this boundary here I forget that if you have 4 wheels is sometimes better. If you have this boundary, okay, this boundary is gonna apply the fixed constraint. So right now there is a equation. What is the equation? That the movement or the velocity of this area is equal to 0. That's the boundary condition for that. You have conditions for, and when I right click on top of this solid mechanics, you're gonna have some that are applied to the domain. What is a domain? The domain basically is a volume, okay? So there are some conditions that are applied to a domain. There are some conditions that are applied to a boundary, one of the edges, and there are some conditions that are applied to a point. So right now I'm gonna add a point load. Where is the point load? The point load is in this specific point here. I'm gonna select that one. And it's gonna say, okay, what I am applying a total force. I can apply other things, but right now it's a total force. In which direction? In the X direction or in the Y direction? I'm gonna apply it in the Y direction. And in the Y direction is gonna be the force that I already create, Fy. Okay, so right now, remember, I have this clamp here, and a point here. So if let me minimize this one second. Remember the problem. It's fixed constraint in this direction and only a point with the force. That's all my problem. And I need to know what is the deflection of this. Okay. So that's exactly what we did. And my screen disappeared. Sorry, here. Now, the direction of the force needs to be in minus Y. Remember, I'm going down, so my force is down. So minus Y, not plus Y, because otherwise the beam is gonna be deflecting up, okay? And now I'm gonna tell the problem, the COMSOL, divide everything in small sections. So I go here to mesh, and I try to define the physics and the mesh, and I'm gonna say build all. Right now, it's dividing the problem in tiny little problems. So in the center of each triangle is solving once the equation. So right now it's doing a very poor job because I'm just breaking this in very tiny pieces. But I can do, this is a normal mesh. Mesh means how many triangles do I have? Or I can do an extreme fine mesh and I say build all. Oh, now it's became a more interesting problem. So here in this section, I can navigate using these buttons and I can use this zoom box and show me the grid in this little area here. Oh, now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 points that I use to calculate the thickness of the beam. That is a more interesting problem. We're gonna do something about this one in a while, but right now let's run the normal and let's build all. If I wanna zoom out, I can go this one, and this is the extension, the zoom extension, okay? Okay. So I define the physics, I define the material, and I define the geometry. Now I'm going to study, and I need to just tell me, like, what are you trying to solve? I am trying to solve the solid mechanics. Right now, it's very simple. We don't have many physics. It's just one physics. And I go compute. And now we have a simulation. What is the result of this simulation? Well, first of all, is presenting the von Mises. That is a representation of the stress. Let's put it in that way. I'm not going to enter in details. And is doing some deflection here. But is this deflection real? That's the first question that we need to ask. So the results of this simulation are going to be presented here. And you can add as many results as you want. So first of all, the results are going to be presented in these databases. So this is the information. I mean, this is the result of the simulation, this database here. This is what you need to be careful of saving. Right now that we finish simulation, it's a good time to do save. And I'm gonna say like the test beam number 2. Okay. And what we are simulating? So we are simulating the stress. And in the stress, the color of the simulation is, it was the solid Mises, and it's in Newton per meter square. So right now, what you're seeing here in COMSOL is the different colors represented on this bar on your right is represented in Newtons over meter square. And the deformation, okay, it's kind of what is changing in the shape of the beam. Well, the deformation has a scale here. So in order to see if we are deforming something that you can see, you need to change this number to 1. It means the scale of deformation is equal to the shape that you are seeing in the screen. Right now, it's a little exaggerated here. What happens if I hit plot? It's gonna show me the real deformation with a scale of 1. So if my beam is 5 microns thick, the deformation of the beam is in terms of microns. And what happens if I hit plot? And this is to answer Rebecca's question. Right now, COMSOL is telling me, like, if you apply 10 millinewtons to this problem, the beam is gonna be deformed 300 microns. Well, is that real?
Professor, is there not a way to apply like the structural integrity of an object in the material settings so that the simulation knows that if it reaches a certain value, like the structural integrity is compromised, and then
very
result
good
is
question.
false?
Yes, it is. Whose job is that?
Ours.
It's your job to include the material integrity. Yes, you can define it. How do you define it? We're gonna see that about on Wednesday. If you have a curve that a measured material, before fracture, you can input that material and say like, from this point to this point, do it. Higher than that point, stop doing it. But please let me go there in a couple more lectures, because I want to get the principle of this. Okay. But yes, you can include it. In fact, you do it here in material. You can add in the material a function or a defined property group. Usually what I do, in definitions, you can add a function. And for example, you can do an interpolation. So you do a measurement in the equipment with that where your material breaks, and then you load that those results into COMSOL, and you say like, hey, make COMSOL behave until this point, and when it reached that level, it stopped working. You can do it, but let's answer that question in a couple of weeks, okay?
Okay, thank you, Professor.
Okay. So what are we gonna do now? Of course, this is not real. Why? Because my beam was 100 microns and is deflecting 300 microns, except if it's rubber, more likely the material has been breaking long time ago. So what are we gonna do? We're gonna do, instead of a single point simulation, we're gonna do something that is called parametric simulation. So for doing that, I'm gonna add in a study a parametric sweep. What is a parametric sweep? I'm gonna make one of the variables changing from different ranges. What variable? The force. And to find out what forces am I getting. So when I add the parametric sweep, I'm gonna add a parameter. And what is the parameter that I'm adding? The parameters that I create here. Remember the force, 10 millinewton? So when I do a parametric sweep, I'm gonna say, okay, give me a simulation from, and you need to press this button here that says range. And I'm gonna use an exponential simulation. Why? Because I'm working in newtons and I wanna know from 1 nanonewton, it means 10 times to the minus 9, so minus 9, up to 1 millinewton, or let's say 10 millinewton, but 10 millinewton was not very good. Let's say 1 millinewton. 1 millinewton is 1 times to the minus 3. Sorry, the stop. In steps of 1. This is exponential. It means times to the minus 9, minus 7, minus 8, minus 9, minus 8, minus 7, minus 6, minus 2, minus 2, minus 3. And I do replacement. So this is a range, okay? And now I can say compute. Now be careful because it already finished. Okay, this is possible. 35 microns, it is possible. And right now I'm having deformations. Look here, the stress. And I'm having multiple solutions. One solution for 10 times to the minus 9 is not deflecting anything. To the minus 7 is not deflecting much. To the minus 6 is not deflecting much. To the minus 5, deflecting a little. To the minus 4 is deflecting a lot. To the minus 3 is deflecting significantly. Okay. So how can I plot this information in something that I can use? And before I move to that plot, do you have any question? Have you been following this path? Do you have the same results?
Yes.
Professor, I didn't understand completely the parametric sweep. Sorry, can you do a quick?
Yes. So what is the parametric sweep? There is one parameter that it was the force that I want to change multiple times. I don't want to simulate only one force. I want to simulate multiple forces. So what I do is add this parametric sweep And in this parametric sweep, I can tell the system where to go. Then let me change this one. Add Fy, that's the parameter, the force in Y, that's the parameter that we want to change. And let's do a range. I can do a range that is linear, or I can do a range that is logarithmic. So let's do a range linear. So for example, I want to do from 0.03 millinewtons to, let's say, 0.1 Newton. 0.1 millinewton, sorry. In steps of 0.03 millinewton. You can define the range as in the way that you want. Right now, I am defining it linearly. Before I define it exponentially. It means 10 times to the 1, 10 times to the 2, 10 times to the 3. So make a broader simulation. So with this range, I can go ahead and compute. And now the results that I'm getting is, let's go to the stress. And the results that I'm getting is the 3 sections that I simulate. 3 times to the minus 5, 6 times to the minus 5, and 9 times to the minus 5. Is the range that I define here in the parametric solution is the number of iterations that the problem is going to simulate.
Okay, but then you can only enter here parameters that you have defined previously, right?
Yes, exactly. So
okay.
you define here in parameters the force, distance, size, magnetic field, whatever, and then you here start requesting for that parametric to happen. So let me go up to 1 times to the minus 9.
And you can simulate multiple parameters at once, right? It'll just do a multiple of their
Yes.
iterations.
Yes, definitely.
Okay.
So minus 9, that's the exponent. Stop in minus 3, it's 1 millimeter. And in steps of 0.2, 0.5, just to have.
Does this also apply to, so I can see like you use this when you want to simulate different forces, but like, for example, what if you wanted to keep the force constant, but then simulate the beam with different lengths or cross sections?
Sorry, can you say it again, please?
Yeah, so I can see how you can use this to like simulate with different forces, but what if you wanted to keep the force constant, but then change the parameters of the beam itself, like each time it computes, you want to change, for example, maybe one of the parameters of a cross section and see the results of that. So you can also do that with the parametric sweep?
Yes, you can also do it with the parametric sweep. It is possible. So I'm going to here 5 steps per decade.
Are most of the simulations in this program pretty quick? Because I know in Cadence, there are some that can go for like hours, especially if you're doing multiple parameters.
Yes, definitely. And that's why I'm trying to encourage you to just do everything in 2D at the beginning. If a simulation at this point, if a simulation is taking more than 1 or 2 minutes, you are in trouble. You are defining something wrong. Especially you are missing one important variable at the beginning. Okay, so yes, be careful and be mindful about that one. You are right. It could take forever, and that's not the idea. Sorry, exponential. Sorry, a minus 9, a step in 0.5, and a stop in minus 3. And let's compute. Yeah. So what I want is to generate, first of all, this is very nice, this is very beautiful, but you're not going to use this in a publication. You need the data. You need what are the forces and what are the displacement related with those forces. So right now, I'm going to add to this results a 1D plot. That 1D plot is just a graph. It's not color scheme, nothing. It's just a graph. And in that color scheme, I'm gonna add, right click, and I'm gonna add a line, a point graph. It means I'm gonna evaluate that point. Which point? This point here. And I'm gonna evaluate the solid displacement of the point. So look what COMSOL is giving me. It's giving me the force, the forces that I use, and the displacement that is moving. Of course, I should get this in logarithmic scale. And now it makes a little bit more sense. Logarithmic scale is this one here and here. So now it's telling me for 1 nanonewton is displacing 10 times to the 4 in meters or in micrometers. This is in micrometers here. If I want to displace 1 micrometer, I should be displacing, I should be applying around millinewtons in general. So the question number 1 for this exercise is I want you to compare the analytical model with this equation that with this figure that we just generated. Okay. So in this figure, we have a line for different forces changing the displacement. For each force, we change the displacement. Let me, oh, sorry, I stopped sharing my screen. For each force, I change the displacement. Now you have an equation. Remember the, let me do something quickly here. I'm gonna copy this one. Come on. I'm gonna copy this one. And we are going to, in the first question, we want this equation. And now the blue line, this blue line is going to be your COMSOL. And I want you to calculate your analytical solution. And I want to see that comparison. That is the first question here. Represent a graph of displacement versus force for 3 different thicknesses. Go there and you can, oh, come on, didn't it record this? I want you to go and make another line for another thickness and record the analytical solution and the COMSOL simulation. And go and do a third one with the analytical and the COMSOL simulation.
Does the COMSOL simulation give an equation for the plot?
No, you need to create the analytical solution.
Okay.
What do you think? It's gonna be so easy? No.
Is there a way to extract the data for this plot and like be able to plot it in like a, for example, Excel so we can like superimpose graphs?
That is a very good question. And yes, you can. So the way that you can do this is you can select the file, okay? And you can copy the plot data to a clipboard, or you can add plot data to export. So you can export it. You need to wait a second. Meanwhile, we search if this computer has Excel. Yes, it has Excel. And here, when you have it here, you can, the output could be a text file no, in this case is better to, sorry, this export to Excel changed with the versions. Like version 5 is different from version 3 and this one is a little newer. So give me 1 second. I'm going to, you can copy plot the data to the clipboard and then you can go here and paste. And when you have this one, you go here in data and text in columns. And the columns are spaces. Oh, sorry, but not the header, just this one. And text in columns, delimited by space and tabs, and finish. And now you have X and the height.
Okay.